At the beginning of this chapter, I talked about the commutative property of partial derivatives. That's where the order of the second derivative of a partial derivative didn't matter, right? So remember, for second order mixed partial derivatives, order of derivatives does not matter. Okay? Alright, and so just to remind y'all about it, if we took the partial derivative of x with respect to y at constant z, and then took the derivative of that with respect to z at constant y, that's the same as saying we took the partial derivative of x with respect to z at constant y, and then took the partial derivative of that with respect to y at constant z. All right, that's just mathematically a property of partial derivatives. Now, jumping to thermodynamics, the same thing applies to the variables in our fundamental equations. Okay? And so, if we just take the fundamental equation of the internal energy, du is equal to TdS minus PdV, and we took the derivative of it with respect to S at constant V, and then took a second derivative of it with respect to V constant S, that's equal to taking the derivative of u with respect to V constant S, and then taking the derivative of that with respect to S at constant V. Okay? All right, so that's just, what the commutative property tells us about this derivative. The reason it's useful in thermodynamics is because, based on our analyses from before, we actually can rewrite these derivatives in terms of measurable properties. And so, if you remember that from before, we said that the partial derivative of internal energy with respect to S is just temperature. And the partial derivative of u with respect to V is just negative pressure. Right? And so what we have here, by using this commutative property, what we could say now is that the partial derivative of temperature with respect to volume at constant entropy is equal to the negative of the partial derivative of pressure with respect to entropy at constant volume. Right? And so that's, by combining these fundamental equations and the properties of partial derivatives, we're able to get this sort of relationship. So this second partial derivative trick that we just pulled this is known as a Maxwell relation. Okay? Right? And we could apply the same sort of trick to other fundamental equations. Okay? All right, and so what we could do here is, I'll let y'all practice, kind of doing these Maxwell relation identities. But for now, I'll just list what they are for each of the fundamental variables. So from the internal energy fundamental equation, if we work out the Maxwell relations, what we get is that dt dv, constant s, is equal to negative dp, the negative outside, negative dp ds at constant v. That's the one I just showed you. If we did this with the enthalpy fundamental relation, what we get is dt dp constant s is equal to dv ds constant p. For Helmholtz, it's minus s dt minus p dv. What we get is, I'll write out the negative signs here, ds dv constant t is equal to negative dp dt constant v, and of course these negative signs will cancel. And for Gibbs, we get dg is equal to v dp minus s dt, and that's equal to negative ds dp constant t, which is equal to dv dt constant p. Okay? Alright, and so this is actually what we were looking for earlier, right? And so from the Maxwell relation, or for expansion of gas, what we could do is we could, in that equation we had all the way at the beginning, what we could do is we could relate or replace ds dp at constant t with negative dv dt at constant p, right? And so this tells us, rather than having to think about how entropy changes with pressure at constant temperature, what we should actually do is actually look at how the volume changes with temperature at constant pressure, right? So that's actually the data that we need to collect. See how volume changes with temperature at constant pressure. That's a measurable. That's something we can measure.